Hey guys, can I get a sound check?
Yeah.
Okay, great, thanks. Let's see. Okay, guys. Wait, it's going slow. So, guys, from an administrative standpoint, we have homework. Homework, I guess, what is it called? It's number 4, but it's basically the problems for chapter 5 it's on the Canvas right now. So if you guys want to start messing around with those. So we're gonna keep going with the biasing. Hopefully just finish it pretty quickly. So, we talked about, again, for biasing, we know it's important to get our amplifiers in the right mode or the right environment before we actually apply the input. So that's all what biasing is about. So far, we've covered a few different biasing approaches and sort of showing the evolution of biasing. And each one of them has its own issues. I mean, they kind of all work, but they're not all usable, or they don't all have the same amount of, I shouldn't say usable, you can use them, but the question is, can you live with the variations? And I think the first few, we couldn't really live with the variations. Let me just go to this thing, which is where we'll be getting to, but this first type of bias was a very simple effort to get a base current to turn on Q1. And it's really simple. It's just got a resistor hooked up to the supply. But as we saw, it has a big dependency on the beta. So basically what this does is it puts a certain current into I sub B, but then I sub C, so I sub C is beta I sub B. Okay, so this sets I sub B. I sub C is beta I sub B, and beta varies a lot. I don't know, depends on your bipolar transistor, but say, it could be as much as plus minus 50% in a typical device. In fact, I think I showed you guys the spec sheet for bipolar transistors, and a lot of times they don't even specify what the maximum beta is. They just guarantee a minimum beta, and the maximum beta is whatever it is. So it's kind of like not very well controlled at all. So that has this danger where you don't really know what your collector current is going to be for sure. The second approach we looked at was putting in a resistive divider. And what this does is if we pick R1 and R2 carefully, so if R1 and R2 are chosen so that I sub B is much smaller than I sub R2. And what that does is it guarantees, or it basically allows you to pretend like this is a voltage divider and this point isn't going to change much with I sub B. If we pick that, then so if we call this point X, V at X is VCC R2 over R1 plus R2. Okay, if this is the case, which is good. The problem is, in this case, resistors also vary. So you can buy resistors or 10% or 1%. I'm sure you can go to higher accuracy resistors, but they get more expensive as you select them. So basically, both of these guys are affected by variations. Another problem that these two devices have, these two biasing techniques have, is that, or sorry, I should say this one has. Well, actually, I think both of them have it. And so there's this one, as we'll talk about a little bit. So today we're going to talk about these two biasing approaches, which are, these end up being what I would call sort of production worthy. Okay, so let's call these guys, so production worthy for various reasons. So another problem that this guy has, and it still shares it with this one, and it does really share it with this one as well, is that VBE also varies quite a bit because of the following. So VBE is VT natural log of IC over I sub S. Well, V sub T changes with temperature. We know that. It's just part and parcel of it, but at least the rest of it, it's like a known variation. It's the rest of the stuff in the V sub T equation are physical constants. But I sub S is also a device dependent parameter, and the manufacturer doesn't control that very well either. So I sub S is also a big variation. And so this is a problem here. It's a problem here, and it's a problem here. So the next biasing thing that we're going to look at is this guy. And it's basically trying to get rid of this dependency on VBE, or at least reduce it somewhat. So what this is attempting to do is to take this, reduce the dependence on the resistor values, and reduce the dependence on VBE. All right, so let's take a look at what this looks like. So this is it's a technique called emitter degeneration biasing. And sorry, did somebody had a question? Didn't catch that. I thought I heard something, but probably just some whisper here. So let's see. See what I want to talk about in that case. So this is a technique called emitter degeneration. And the first thing, so again, I think what you want to do is to make this current it shares the same thing, you know, in the case where we didn't have this, this just went to ground. You want to make this current through here much bigger than I sub B. So they share that together, and it sort of does this resistive divider operation. But the main difference with the previous one is X is no longer VBE. Okay, so note, this is a very important thing, and it's easy to forget when you're doing, note, V at X is unequal to VBE in this case. And the reason for that is we've hooked up the emitter to a resistor going to ground. Okay, so it's no longer, the emitter is no longer at ground. And so this ends up being, you know, something that trips people up, is make sure you realize that the base emitter is actually the difference between this point X and let's call this point Z. Okay, so, and then Z is dependent on some things. Okay, so the major idea behind this approach is that, you know, in the case where we had this, now let's see. So let me just, so let's draw it here. So in this case, where we just have the emitter grounded. In this case, I sub C is I sub S exponential of VBE over VT. And notice, so notice any changes, any variation, so any variation in VBE gives you an exponential variation in I sub C. So if you remember, just a 60 millivolt variation in VBE gives us a 10x change in I sub C. That's a huge variation. So, you know, by the same token, if you had 20, 30, 40 millivolts of change on VBE, which, you know, could be very easy to get, you'd have a huge variations in I sub C, which isn't good because I sub C changes your gain, right? Just directly, because, so this is changes gain significantly. Because GM is I sub C over VT, and gain is G sub M R sub C. So we get huge variations in this case because we have this exponential dependency. So in this case, by putting the resistor here, which is, by the way, called emitter degeneration, and I'm not sure why it's called degeneration. It's basically reducing, what it's doing is, it is making this current, I sub C, be dependent on, closer to being dependent on a resistor value. So let's look at it. So what happens is, think about the current I sub C. So we know I sub E is I sub C plus I sub B. That just, you know, we had that earlier on when we talked about the bipolar transistor. So that is this current I sub E, which is the same current that runs through R sub E. So that's this current plus this current. So this goes into the collector, this goes into the base, and they flow out of the emitter. So I sub B, we know, is, we don't know the exact value of I sub B because it's, well, let me just write it. It's basically I sub C plus I sub C over beta, which is I sub B is I sub C over beta. Now, we don't know the exact value of beta, but we know it's always guaranteed to be a fairly large value. So you could say that I sub E is approximately equal to I sub C, because although beta is all over the place, it's much greater than, say, let's call it greater than 50. So it's a big number. Okay, so basically you can just say I sub B is very approximately I sub C. Okay, so or conversely, I sub C is the same as I sub E, right? Again, all I'm saying is I sub B is very small compared to either I sub C or I sub E. Okay, so now look, think about this current I sub C, assuming it's the same as I sub E. Again, just being very small. Okay, what is it going to end up being? Well, I know I'm dropping this voltage VXZ. Okay, so the voltage here is X. There's a VBE drop, so VZE. So VBE is V sub X, sorry, take this back. V sub Z is V sub X minus VBE. Okay, and I sub E, which is equal to I sub C, approximately, is equal to V sub Z over R sub E. So notice here what happens if V sub BE changes by 60 millivolts. Okay, so in this case, if VBE changed by 60 millivolts, then I get a factor of 10 change in collector current. Here, if VBE changes by 60 millivolts, VZ changes by 60 millivolts, okay? And that's like a 60 millivolt change across a resistor. So it's no longer a exponential change. It's like a factor of like a few percent change, or at least 10, 50%, less than 100%. So let me show you guys an example. Let's say I picked, so example, let me pick an example. So example, let's compare this case. Compare this with this. Okay, and let's see what in case that VBE varies by 60 millivolts. Okay, so let's say for the sake of discussion that in both cases, in one case, so in this case, V sub X, I tune it to be whatever, it doesn't matter what it is really, because we're looking at a delta. Okay, so let's say it's 860 millivolts, and so delta Vx is 60 millivolts, and V sub x, let's call it V sub x, V sub so let's call V sub x high is 860 millivolts, and V sub x low is 800 millivolts. What I mean by that is we're saying that in production, say, or if you make 1,000, 2,000 of these devices, sometimes the V sub x could be 860, and sometimes it could be 800. Okay, or let's say VBE varies by that much. Sorry. So let's say 8. Sorry, but take it all back. Sorry. We're saying V sub BE varies by 60 millivolts. So let's say we've got set V sub x at 860. What I said earlier was correct. Okay, so V sub BE high is, let's see, as in one case, it's 860 millivolts. And in one case, VBE low is 800 millivolts. So I sub C at VBE low is 10 times I sub C at VBE high, which means gain at VBE low is 10x higher gain at VBE high. And also your voltage at this point is going to be quite a bit lower, right? Because you have 10 times more current going through R sub C. So V sub C at VBE low is going to be, it's going to be 10 times smaller, or it's just going to be significantly lower than V sub C at VBE high. Does that make sense, guys? The point I'm trying to make there? Or is it getting too confusing? What I'm basically saying is if you have this expected change in VBE by 60 millivolts in this case, you're going to get a significant change in I sub C, which is going to significantly, by a factor of 10, which is very, very significant. So it's going to change your gain by a factor of 10, and it's going to change the voltage here significantly, because in one case, you're going to get 10 times less current dropping, or IR dropping through here than in another case. Okay, so this has got huge amount of variation, exponential variation, like we mentioned, right? Because of this I sub C is I sub S exponential of VBE over VT. Now let's look at this case. So in this case, let's say I make V sub X be, what should I make it? Make it 1 volt, okay, approximately. So let's say we set it to be 1 volt. Okay, so now let's say VBE changes between 860 and 800. So V at Z goes from, so VBE, V sub Z, oops, V sub Z high is 1 volt minus 800 millivolts. So that's 200 millivolts. And VZ low is 1 volt minus 860 millivolts, or 140 millivolts. Okay, so in one case, you have I sub E, and this is equal to IC. So I sub So I sub E high is 200 millivolts over R sub E. And I sub E low is 140 millivolts over R sub E. Okay, in this case, and this is also equal to I sub C in both cases, right, approximately. So the point being, in these cases, although the current I sub C does change, so I sub C changes as well, but not by 10x. So let's say, for example, let's say RE is 100. Okay, what does this give me? It's gonna give me, it's a lot of current. Let's call it 1K. Calculate this. Is that right? 200. What am I doing? 200. Okay, now let's call it, let's say R sub E is, we make it 100 ohms as an example. So IE high would be equal to 200 millivolts over 100 ohm. So it's equal to 2 milliamps. And IE low would be 140 millivolts over 100 ohms, or 1.4 milliamps. So that would be 2 enter 1.4 subtract. So that's a 30% change in this case. And I guess in this case, you would call this 1000% change in I sub C, in I sub C. Okay, and gain. Okay, so what you're doing is by degenerating so-called this emitter, you still get a variation because of VBE, but the RE, I mean, it's sort of a very nice way to put it, that RE helps absorb the error in V sub X, okay, and VBE. So basically what happens is, even if V sub X varies, V sub BE varies somewhat, you still, R sub E basically gives you a linear dependence on that change rather than an exponential dependence. Okay, does that make sense, guys? Any question about that? So that's a really, really important point. And I really think this is, as you'll see, this is, changes also the gain of this stage. So not only are we biasing this stage differently, but as you will see in the next set of slides, we're also changing the gain of this, which is no longer just this thing, but it does vary it, but it gives you this enormous benefit in terms of reducing the variation. So any questions, guys? Okay, if not, I'm going to go to the next one. So this is my favorite, I guess. I think this would be my favorite biasing approach for bipolar transistors. I mean, for single-ended bipolar transistors, because it's got all those ingredients. And as you'll see, not only is this makes your biasing more immune to variations, but also there's an effect on the gain. Your gain actually goes down with this topology compared to the common emitter, but you have really big improvements in your gain variation also goes down significantly. So gain variation goes down, biasing variation goes down. You got better linearity. We haven't really talked about linearity much in the class, but that's a pretty big figure of merit for analog design. Imagine anything that's nonlinear gives you distortion. Again, using audio as an example, we kind of know distortion is not, sometimes maybe you want distortion for some sound effect, but generally it doesn't give you a true reproduction of the sound. Okay. And then lastly, as we'll talk about, it also changes the input impedance here, makes it higher, which is also a good thing, as we remember. So a high input impedance is good for an amplifier. So this approach, I think, is my winning, is my favorite personally. Okay, so there's another approach called a self-biasing technique. This one's pretty simple to understand, and it's pretty simple, as a concept. The nice thing is, so I'll talk a little bit about it qualitatively again. The nice thing is it guarantees that this guy always stays in forward active mode. Okay, so guarantees is in forward active mode. So why does it guarantee that you're in forward active mode? Because what you've done here is you've connected this resistor from the collector to the base. Okay, so you're always guaranteed that no matter what happens, so VB is always, let me say VBE. VCE is always greater than VBE in this case, right? Because VB, IB could be anything big or small, but the voltage here, because you get a resistive drop across R sub B because of IB, you're always guaranteed that this voltage is going to be below this voltage. So no matter what, this guy is going to be in forward active mode. Okay, as long as you have enough, if VCC is large enough. Okay, so this is kind of something you don't have to, I guess if I had just a few minutes to get something working, this would be like a good way to go about it. Just connect a resistor from Y to X, so from collector to base, with a few caveats. You got to be a little bit careful. But like, for example, you could turn off the bipolar transistor if Y was so small that this, and R sub B was large enough that this VBE dropped too much, right? Because if you're at, say, if this guy is at, I don't know, 600 millivolts or something, for whatever reason, then you could get into a situation where this guy gets to, less than 500 millivolts or something. And you just end up having very little current through this device. Okay, so, and the other thing is, I'm not sure how much of a, so I think you got to be a little bit careful, but it works pretty good. It has the You know, it still has the problem. So, you know, it has a couple of guidelines. So the R sub C has to be much larger than R sub B over beta, because you don't want, you basically want this I sub B to be, so let me just write it down here, because goal is to have I sub B not change I sub C too much. Because you remember, you're sort of stealing current from I sub C, some of it, or stealing current from R sub C. Some of it is going here and some of it going to this point. If this guy is too close to this guy, then you're going to get a significant current, significant amount of this current is going to flow into I sub B, which isn't good. Okay, and then you also want to make sure that you know, your VCC is high enough that this guy basically essentially stays on. Okay, so doing all that is good, but you know, I think so. These are the two options for biasing. Personally, I like this one because, as you'll see, I also like the degenerated emitter amplifier configuration, because this also stabilizes your gain, and it's a more of a known quantity. This one again also works. It's the biasing itself is simple, and creates sort of you're not as dependent on beta variations or VBE variations. But the problem with this one for me is that you still have this common emitter amplifier stage, and that the gain of that by itself varies. So, you know, this to me is like a better overall circuit than the common emitter as an amp. Okay. Any questions about that? I wanted to say, if you guys don't have, so these are basically, so the upshot is, you know, use one of these two guys. Okay, so I wanted to say one more thing about biasing of this type of biasing, okay, of bipolar amplifiers. So let's say you have this is your circuit. So now we've biased our bipolar properly. How do we get the input in here? Okay, so we could plug in the sort of, say, call it VN into here. Okay, and let's say this is, you know, this is sort of our 10 millivolt, 20 millivolt, whatever variation, right? The input we're actually going to amplify. But the problem is, if I actually had an input, if I actually did this, if I put a voltage source into this input, I would probably screw up the biasing, okay? Because these things have their own, you want to basically not have the DC value of this thing affect this point. They're only interested in the AC variations in VN. So we are almost always only interested in AC variations in VN. Okay, so what are AC variations? Are things that are changing with time. So the biasing is what's DC, what's constant, and VN is what changes with time. So how do I deal with this situation? How do I not have this input, let's say that's my microphone or whatever, plug straight into here and screw up my DC bias in here with whatever DC needs this has or DC variations it has. So the way you do that is by, and we'll talk about this in the next set of slides in more detail, but I just wanted to give you guys the heads up in case this questions come up. What you do is you put a capacitor on the input. Okay, so what does a C-in do? If you think about the resistance of C-in. So basically the impedance of C-in is, so we have basically J omega C, where omega is 2 pi F. Okay, so with higher and higher frequencies, the impedance of this guy goes down. Okay, so if C-in is large enough, you can consider it a short in AC, so, and an open in DC. So it's always like, looks like an open circuit in DC. If you have a voltage here.
Professor?
Yeah, go ahead.
I thought the impedance of a capacitor was like negative J over omega C. And the inductor was J omega
Well, thank you. Sorry. Yep, you're right.
Okay.
Minus J over omega C. You're right. It's actually J omega C, right? Thank you. So it actually, the higher the resistance is, so impedance. Thanks for clarifying that. The higher the C is, the lower this impedance. So if I have a very high value C and my frequency is high, this resistance goes down and this turns into a short. Okay, thanks for clarifying that. So basically in AC, when you have any amount of input frequency at all, you can pretend like this is a short, but it always blocks your DC value. Okay, so if this guy is not changing at all, so it's a DC value, it could be 100 volts, it could be 1 volt, it could be whatever, but it's steady, it doesn't change with time, then R1 and R2 set this voltage here, okay, for something that's not changing here. As soon as you have any change in input here, which is the interesting, say, microphone information or whatever, what it looks like is a short through, and this guy basically gets the input to this guy. Okay, and we're gonna look at that in detail. Okay, any questions, guys, about biasing? If not, I'm gonna go to, let's see, slide deck, is it? No, it was slide deck 8. Oops. Okay, so now we're gonna sort of talk about the amplifier. So starting with I'm gonna go through the common emitter. I think we've beat that pretty much to death, especially the early, sort of the core ideas. I think we beat that pretty much to death, but basically talking about it, I wanna sort of quickly get into with biasing, what happens with the biasing effects, okay? But let's start talking about the many options of bipolar transistors. So bipolar transistors have, and same with MOS transistors, there are 3 terminals. So bipolar transistor has 3 terminals. That means there's a lot of different ways you can connect the base, collector, and the emitter either together to, resistors, capacitors, or other voltage sources. Okay, but it turns out that there's only really kind of, so for example, you can take, and so there's many different places you can put in the input, there's different places you can take the output, there's different places that you can, again, put resistors and voltage sources, etc. But it turns out there's only a few different configurations of input and output that are useful, okay, that do useful things. Okay, so in terms of the input, there's only a few different configurations that are useful. I think the ones we already talked about were the common emitter and sort of what I would call common emitter includes degeneration, but the idea is that, so input is applied to base, output is taken from collector. Okay, now you might hook up a resistor to the emitter, degenerate it, or hook up the emitter to the ground, but that's sort of like the configuration. So essentially it looks like some variation of this. So input is connected to the base, output is taken from the collector, and again, this emitter here can either get connected to ground, can get connected to a resistor, maybe it might get connected to a current source or something like that, but that's what a common emitter configuration has. Okay, so another configuration that's useful is so-called emitter follower. So we touched on this a little bit, and in this case, earlier, so input is base, and output is emitter. So it looks like, let's see which one of these is. It looks like this one. And, I guess the input is, so we want to put in VN here. Okay, that's what it looks like. So this common emitter has good gain, good input impedance. So check. So high, but the bad thing is got high output impedance. So it's not particularly good to drive low impedance nodes, okay? This emitter follower has gain, so it has, call it gain of approximately 1. So it doesn't, we can't really use it for gain, the gain of the signal. So the gain, it's really a gain of 1, very close to a gain of 1. It has good input impedance. So that's good. Or so I should say, instead of good, I should say high input impedance. Both of these cases. So and it's got low output impedance. Dense. So what this means is this is a good buffer. And what is a buffer? It's something, a buffer is something you put between two stages to help you interface the two stages. So for example, a common thing you'll see is you'll have a two-stage amplifier. The first stage will be a common emitter, which is easy to drive by source because it's got a high input impedance. It'll have a high gain. And then you'll drive an emitter follower with that stage, which is easy. It's got, you know, this emitter follower has a high input impedance. So the common emitter can drive it, although it's not a good driver, but this has got a high input impedance, so it's drivable by the common emitter. And then it has a low, the emitter follower has a low output impedance, so now it can drive, you know, your output, whatever your output load is, even if that output load is low resistance. So that's kind of, these two are particularly popular stages or amplifier topologies in bipolars. There's a third one, which you'll see, you know, you see a lot less of. Is that true? Well, no, I think you see it in some configurations, but it's the common base. Okay, which is you put a input is typically the emitter, output as the collector, and base is used for biasing. And this is, I don't know if we're going to get to talk about this much, but this is used for also for sort of affecting your, how should I put it? It's used in the circuit configurations so that you can increase your gain. But you know, it's kind of complicated, so I won't go into it much. But these are the three main ones, I believe. So common emitter, emitter follower, and the common base. Okay, so let's talk about the common emitter. So, you know, we've talked about this quite a bit already. So the common emitter means the emitter is somehow the reference point. Now this could be without degeneration. So this is the straight common emitter. The emitter is grounded. Input goes to the base, the output comes from the collector. And sort of and again, we went over the small signal amplifier topologies. The gain is this gain equation. So once you have this thing biased, once you know your bias point, once you know your I sub C, then it's pretty easy to come up with the gain as just G sub M times R sub C. And G sub M is I sub C over VT. So but really, you just have to make sure that you've got the right I sub C that you need and that your voltages don't. So make sure you have correct I sub C. Then your gain is pretty straightforward. So A sub B is G sub M R sub C. So that's pretty straightforward. And R sub N is equal to R sub pi, which is beta over GM. And then the third step is make sure transistor VCE is greater than VB. Okay, after you're done, you just got to make sure that it stays in bias, okay, with all those things. Okay, so now, you know, the book likes to talk about the, you know, the maximum gain you can achieve on common emitter voltage. I guess it's important to think about it somewhat, but you know, usually end up with lower gain than this for various reasons because of input output impedance. But if you think about it, you know, sounds like you can kind of make the gain of this anything you want, right? If you change, it looks like, you know, I can change IC all I want, right? I can basically tune it with the right biasing to give me a G sub M as big as I want. And I can even use an RC as big as I want to get a high gain. So there's no limitation to the gain from this circuit, well, from this equation. It looks like that's the case. But in fact, the limitation on the voltage gain ultimately comes from your so-called headroom. So what's called headroom limitation. So this headroom is a term you hear a lot in analog design, and basically refers to how much, what's the voltage variation between VCC and Vout. So max voltage allowed between ECC and Vout. I'm not sure I'm putting that the right way in terms of English usage, but look at the idea. If Vout, let's say you have your VCC is very low, right? So example is, let's say VCC is 1 volt. Okay, so you know I need at least 800 millivolts here or something. Let's say 800 millivolts at the base to have this guy be in forward active. My Vout can't be much lower than this 800 millivolts, right? So the Vout, the minimum Vout, let's say minimum Vout. So this sets minimum Vout at approximately, I don't know how much you want to call it. Let's say it's 700 millivolts. Okay, so let's say your input was, say, input is 20 millivolts max. So the maximum output that you can, the maximum output swing that you can sort of take into use is 300 millivolts, the maximum gain that you can get out of this is a gain of 300 over 20. So maximum gain is 15. So why is that? It's because on the low side, I can only go to 700 millivolts here. And if I go any lower than that, this guy starts coming out of forward active mode. But I can go higher than that, but I can't go any higher than VCC. So the maximum voltage swing I have here is 300 millivolts, from 700 millivolts all the way to 1 volt. So let's say I can go all the way up to 1 volt. It's difficult to do because my I sub C would be 0, but so let's say maximum value would be 1 volt, right? In that case, my maximum output swing would be 300 millivolts. And let's say my input is 20 millivolts max, then the max gain I can get is 15, regardless of my GM or anything like that, okay? Hey guys, can you hear me okay? I noticed my video is frozen.
Yeah.
Okay, great. So that's the idea. So you can go to higher gains if you make let's say now so let's make VCC be 2 volts. In that case, my highest delta V out variation is 2 volts minus 700 millivolts. So it's 1.4 volts, no, 1.3 volts, sorry. 1.3 volts, so the maximum gain I can get in that case is 1.3 volts over 20 millivolts. So that's a gain of 65. So that's the max I can get in that case, just by increasing VCC. Okay, so this is what this means, is that this headroom, so that basically the difference between VCC and V out, I guess, again, I don't know how else to, how to put it. I don't know why it's called headroom. I guess maybe this is on top. So it feels like the headroom, I don't know, like how much headroom you have for the V out to go up. Okay, sets the maximum practical gain. Now, why not make VCC just crazy high, like make it 100, just so that you can go to a very high gain? The problem is usually VCC is limited because of power consumption. So the power consumption of the circuit is VCC times IC. So the higher I make VCC, the more this circuit is gonna power it's gonna consume. So, which is important from, if you've got this thing in a portable device, like a cell phone, you've got it in your smartwatch, you got it in your pacemaker inside your body, you're gonna basically drain that battery faster. So going from 1 volt to 2 volts, all things being equal, your battery is gonna drain twice as fast. Okay, your power consumption went up by 2x by doubling VCC. Okay, and if you're not in a portable situation, that power typically just translates into heat, and there's only so much heat you can economically remove from your circuit. So in all cases, power consumption is really important. Okay, so we kind of talked about this in terms of headroom. So in terms of, so that's sort of the maximum usable gain between, how much gain you can have in your headroom. I think we already looked at the input-output impedance of the common emitter amp. It's pretty simple. Again, so this is a small signal for the amp. You put in a perfect voltage source on the input and measure the current going through that voltage source, and it turns out that the input impedance is just R sub pi. So an R sub pi is beta over GM. So, this input impedance typically ends up being hundreds of ohms to kilo ohms, so several kilo ohms, depending on the values of GM that you get. And the output impedance without, so this is without early effect. The output impedance, you do the same thing. You put a perfect voltage source on the output. You measure the current going into the input, except in this case, you also short the input. You have to remember to short the input. You analyze the circuit, and you just get, again, without the early effect, you get the load resistance as the output impedance. And notice, because you want, some amount of gain, this R sub C is going to be, depends on how much gain you want to get. But this R sub C, you're not going to make it too low. It's not going to be 1 ohm or 2 ohm or whatever. It's going to be, probably in the hundreds of ohms to kilo ohms to get reasonable gain. And that means that you're going to have a hard time driving low impedance loads because this value needs to be relatively high to get decent gain. Okay, so these are the trade-offs you have in a common emitter when you're designing a common emitter voltage. Okay, so you're trading off the amount of voltage headroom you have. So the supply voltage or the voltage swing you can get for a certain input with voltage gain. Okay, so you could be trying to design things in for a high voltage gain, but if your supply voltage is too low, you can't really use all the gain. You can try to increase R sub C to increase your gain, because gain is GM R sub C. But the higher the R sub C value, the higher your output impedance, means you're going to have a difficult time driving loads. Okay. And then you can also try to increase your G sub M to get higher voltage gain by the same token. But because your input impedance is beta over G sub M, every time you increase G sub M, you're reducing your input impedance, which is not good for loads driving you. So these are all sort of trade-offs in a common emitter stage. Essentially, it's power consumption, output impedance, input impedance, and all of it traded off against voltage gain. So you'd only use this common emitter stage if you want voltage gain, and these are your limitations. Okay, problems with driving input and output and power consumption. Okay, so if you add the early effect to the common emitter model, it's got like a very simple but unfortunate effect is that, well, I don't know if it's an unfortunate effect. Well, it is an unfortunate effect. So basically you just end up sticking this R sub 0, which is this early effect voltage. So remember, this was, I think R sub 0 was V sub A over I sub C, okay, where V sub A is the early voltage. And the unfortunate effect is that this just goes in parallel with your R sub C, which is your load resistance. So it drops your effective resistance, because now the gain is G sub M minus G sub M times these two resistor values in parallel. So it ends up reducing the overall gain. Okay, and you know, again, the book talks about intrinsic gain. I'm not sure that's important. The current gain, I guess it goes, I don't know, this to me goes without saying, you know, we've got the output current over the input current, and almost, I guess by definition, I out is I sub C in this circuit, and I in is I sub B, and that ratio is beta. So fair enough. Okay. So we just sort of quickly, I was sort of jamming through this common emitter stage because I think all of it is review. So to get us to emitter degeneration. So I'm not gonna go into, so I think we're gonna have to wait for Tuesday to go into details of emitter degeneration. But let's just sort of to give you guys an overall view of it. And this is kind of the same idea we talked about a little bit when we talked about the biasing, the effect that this emitter resistor has on the biasing. And it really has the same, it's the same idea for the gain in some sense, that what's going on is if you have an input voltage, some of it, so remember the way fundamentally fundamentally the way we have gain in this circuit, the way we have voltage gain, is we put a change in voltage here. This change in voltage gives you a change in current on the output. And that change in current times a resistor that's also hooked up to the output gives you a change in the output voltage. Okay, so change in input voltage, change in, whoops, it goes in reverse, change in output voltage. So this is sort of fundamentally how things work here. And so when this change in input voltage gives you a purely exponential change in current, because if we had this guy connected to ground, if whatever voltage changed here, this guy's grounded, so whatever voltage changed here, this current, this output current changes exponentially with this change in voltage. An exponential basically means a lot. So you can get a lot of gain. You know, that small bit of voltage change here gives you a big change in current, and that big change in current times a resistor gives you a big change in voltage out here. So high gain, get that? Okay, so that's really good. The problem with it is, just like the biasing circuit we talked about, there's a lot of variations in that gain. Okay, so if you have this change in voltage, it's exponential, but it's kind of somewhat uncontrolled, because that exponential dependence, so that I sub C, I sub S exponential of VBE over VT, this thing has, it's good, it's got a big change in, a big change with VBE, but it's, you know, dependent on, you know, this current, it's dependent on variations in VBE. It's got variations with temperature. So all sorts of stuff's varying here. It's all large values, but it's all over the place. Okay. So the idea is, by putting in a resistor on the emitter, the idea of degeneration is by putting a resistor in the emitter, we put only some of this voltage change on the VBE, and the majority effectively ends up being dropped on the RE. Okay, so you basically go from this exponential dependence in change in current. So let's say, so I'm going to say delta I sub C is exponential delta VBE, to the case where delta IC is delta V sub E over R sub E. So let's call this delta Vn. So this is common emitter. This is common emitter with degeneration. And everything is like approximate here. Okay. So the idea is the majority of your change, you know, some of your change in current is still gonna be because of VBE change, but most of it, again, depending on how you pick your R sub E values, et cetera, is majority of your change in collector current. It'll be because the voltage drops across a resistor. And so it's much more controlled, because that way you can just make that be, as we'll see, A sub B will be approximately RC over RE, very approximately. Okay, we're gonna have to give that some more nuance. So what happens is your gain is dependent on the ratio of two transistors and not on this gain is G sub M R sub C. So this gain is dependent on, you know, a current that's difficult to control. This is dependent on the ratio of two resistors that you can make to be from the same material, they're sitting at the same temperature, so on and so forth. So your gain can be a lot more controlled. The problem is it won't be as high because you're not going to have an exponential change in current, collector current. You're going to have closer to a linear change in collector current with change in Vn. All right, guys, so that's just sort of a heads up for our next class, where we're going to talk about the sort of looking at deriving how this works in a little bit more detail. But just again, same idea as the biasing, is this approach gives you lower gain. So it seems counterintuitive to use it, but that lower gain means it's much more controllable, much more producible, much more production worth. Okay, guys, any questions? If not, I'll let you guys go. Have a great long weekend, and I'll talk to you guys on Tuesday.
Thank you.
Thanks.